It's not the perfect die. It's fiber laser heat and test before the systems fly. How do we package photons at the volume AI demands? How do we scale the light with machines, not human hands? Cost per gigabit, cost per port, yield must rise or the roadmap falls short. How do we package photons and build a future on time? Bring the light to the package. Bring the package to the light. PICs can change the market, but only if they ship. Not one by one in clean room dreams, but fast, precise, and fit. Fiber arrays must find their place. Lasers locked in tight. No good die before the build. Thermals held just right. Datacom shouts the loudest, but it is not alone. Quantum sensing lidar defense need packaging of their own. How do we package photons at the volume AI demands? How do we scale the light with machines, not human hands? Cost per gigabit, cost per port, yield must rise or the roadmap falls short. How do we package photons and build the future on time? Bring the light to the package. Bring the package to the line. Hey, foundries and OSATs, equipment on the floor. System teams are waiting, they need more, more, more. Alignment automated, interfaces agree. Wafer level testing at industrial speed. Not a demo, not a slide, not a promise, still untried. Ports must ship, lasers survive. AI factories need light alive. How do we package photons at the volume AI demands? How do we scale the light with machines, not human hands? Cost per gigabit, cost per port, yield must rise or the roadmap falls short. How do we package photons and build the future on time? Bring the light to the package. Bring the package to the line. In just a few minutes, Optica brings the industry to discuss the real test. Please stand by. Package the photons. Scale the light. Build it for volume. Build it right.
Welcome to a packed Optica online industry meeting. Today we're asking one direct question. How do we package photons at the volume AI now demands? AI infrastructure has a packaging problem. Hyperscale GPU clusters need optical I/O on the package itself, not at the faceplate. NVIDIA's Quantum X and Spectrum X switches are early proof that the industry has accepted this direction. But shipping an announcement is not the same as populating an AI factory with hundreds of thousands of optical ports, ready in time for the next GPU launch. Photonic's packaging has historically been slow, low volume and handcrafted. GPU deployment schedules are not. That gap is what we're here to close. Packaging is also the dominant cost in a photonic integrated circuit. Assembly, fiber attach, laser integration, and test account for the majority of a module cost. Until packaging industrializes with wafer-level processes, automated alignment, and known good die testing, PICs cannot cross from niche to volume market. And the same bottleneck is blocking multiple industries simultaneously. Datacom is the loudest voice, but quantum, biomedical sensing, LiDAR, and defense face identical constraints. Solving this once unlocks all of them. In the next 90 minutes, we'll work through the specific problems. And to do that, we've brought together two groups of experts. On the technology integrator side, Nokia, NVIDIA, Jabil Photonics, and Light Matter. On the technology enabler side, Photon Bridge, Epiphany Design, Verna Leap, Fix Photonics Assembly, Finetech, and Cellerprint. This meeting is free to attend, made possible by our sponsors, Fix Photonics Assembly, Ligentech, Vanguard Automation, Nanoscribe, Finetech, and Photon Bridge. So let's get started.
Hello everyone and welcome. Welcome to a very special session. We have been working very hard over the last months and we have seen record numbers on registrations because we are talking of perhaps the biggest challenge that the photonic industry is facing. Many of you were with us at OFC and you saw the huge boom in demand driven by AI. And we saw the need to change the way that we have been dealing with photonic integrated circuits. It's all about advanced packaging. It's all about volume testing. It's all about scaling up. And today we have a fantastic 90 minutes of your time to make sure that during the next 90 minutes, you do business. Today, as very well the intro video said, we are sponsored by Fix, Ligentech, Vanguard Automation, Micronic, Nanoscribe, and Finetech. Thank you very much for making this meeting free for everyone in the room, everyone watching in the YouTube, and everyone accessing this video on demand for as long as we leave it there and we have no intention of ever taking it out. We also would like to remind that we do have two groups of companies. Nokia, NVIDIA, Light Matter, and Jabil Photonics came here with a shopping list. They came here because they need the rest of the companies in the room. And those rest of the companies in the room are everyone with us, including Cellerprint, Fix, Finetech, Werner Leap, and Epiphany Design. Thank you very much for being with us, but everyone in the room is welcome to answer the needs of Nokia, NVIDIA, Light Matter, and Jabil Photonics. We do this because we love our corporate members. If you are not yet a corporate member, what are you waiting for? Optica.org/join corporate. There you can find all the amazing membership benefits, but the most amazing membership benefit is being friends with Dr. John Pugh, who put together this fantastic agenda. This is only part of our agenda of online industry meetings. In a couple of weeks, we have high volume, so we have photonics for energy, then we have 3D sensing. We're going to address topics like ophthalmology, applied imaging, aerospace, quantum safe networks, extended reality, new space, quantum computing, and CPO. If you are interested in any of these topics, make sure you register as soon as possible in optica.org/industry. Please register as soon as possible so we make sure that we answer and we draft the agenda of the meeting facing your needs. And if you want to meet us face-to-face, in a couple of weeks only, 2nd and 3rd of June, we are all of us going to Brussels for the Global Advanced Manufacturing Alliance, the Gamma yearly event. We have a fantastic group of people there, including one of our keynotes today. Liron from NVIDIA will be one of the opening keynotes at the Gamma meeting. If you want to meet him in person, and I do, go to Brussels on the 2nd and 3rd of June. Also on Quantum, 16th, 17th of June, we go to Glasgow. Together with Quantum 2.0 of Optica, the Quantum Industry Summit is looking to attract the CEOs of the quantum companies and see how we can make their supply chain resilient with photonics technology. Do not miss this one. Also, Everyone is waiting for this one, the PEC Summit. What happens in the Juniper Dome stays at the Juniper Dome. This is what we discuss with the key companies in AI-driven networks, how we can bring photonics to satisfy their needs. Do not miss the PEC Summit in October. And last but definitely not least, in December, we go to Paris to talk about perhaps the biggest upcoming market for photonics in Europe, defense. We're going to address this with some of the tier ones, with some of the primes of defense industry in Europe. And of course, our flagship event. Where do we go every year? We go to Malaga. 24-25 September, the Global Photonics Economic Forum. We already published a list of keynotes. I think you are all amazed. No spoilers here. globalphotonicseconomicforum.org. Go there and see the fantastic list of keynotes we have just published. But I would like to remind everyone that today is all about advanced packaging and volume production of photonic integrated circuits. So this meeting is also live streaming YouTube. So let me say hello to the YouTubers in the world. Hello, YouTubers in the world. If you have any questions or comments, write them in the chat and I will read it in the Zoom room. And of course, this is also valid for the people here with me. 159 people here with me in the Zoom room. If you have any comments, questions, challenges, please write in the chat. We'll make sure that you voice the question out loud so the other 159 people in the room can hear you. Thank you very much, all of you, for this fantastic patience that you have for this introduction. John Pugh, what's going to happen in the room over the next 90 minutes?
Thank you so much, Jose, and hello, everyone. I'm particularly excited today about hearing how the industry is moving beyond thinking deeply about individual devices and starting to solve that real manufacturing and integration challenge needed to bring photonics to scale. One of the crucial ways that's happening is by using that experience from the semiconductor industry and incorporating the experience of those who have been there and done it before. The challenges are of course different, but it's clear to me that that experience translates. So as Jose said, this is a very interactive meeting. Post your questions in the chat. We'll welcome you to unmute and ask your questions directly. So let's get straight into it with our first speaker. And for the first time at an Optica meeting with Nokia, Armagan Esagi, Director of AI Data Center Networking. Armagan works at the intersection of AI infrastructure, high-performance networking, and next-generation data center architectures. And today, she'll share Nokia's perspective on how AI is reshaping networking requirements and where photonics and advanced interconnects will be critical to future scale. Armagan, please share your slides. The floor and the attention of everyone is yours. Thank you.
Hey, great. Just make sure everything is okay on the slide. Okay, perfect.
All fine.
Great. Thanks for having me. I'm Armagan Esagi from Nokia, and today I'll focus on the key challenges of photonic packaging and integration, and what we need to make photonic integrated circuits economically viable at AI scale. Well, there is a lot to talk about, but given the time constraint, I'll focus only on the most fundamental aspects of packaging and integration. From a Nokia perspective, this topic is very timely as we run both a silicon photonics line and indium phosphide fab, and we build coherent as well as IMDD modules, components for intra and inter-DC interconnects with diverse capabilities, including monolithic indium phosphide PIC with integrated lasers, multi-chip platform, hybrid integration, advanced packaging and manufacturing, and any advancements in packaging integration techniques enabled by partners' ecosystem will accelerate developments and reduce the time to market for us. So let me start with the premise that the industry is acknowledging today, that AI infrastructure is becoming increasingly interconnect limited. Introducing different variants of optical interconnects has been a way really to address this challenge. So the direction is pretty clear, but there are several challenges that slow down this transition, and we're still far from that scaling point. So over years, we've made significant progress in photonic integrated circuits design, but the packaging tax, which is the cost and energy required to couple the light off the chip into fiber, still remains too high. And by some estimates, packaging accounts for more than 80% of the total module cost. And it gets even harder in co-packaged optics, where you can have multiple photonic suppliers in one package. You have massive fiber counts and the huge yield throughput and cost pressure at a scale that the industry has never designed to handle. So the real objective here is really to move photonic packaging away from the bespoke processes towards a foundry-aligned, high-volume manufacturing model. And my focus today is obviously AI networking, but the same packaging gaps show up in sensing, quantum, biomedical photonics, and so fixing them really lifts the whole field. The first challenge that I want to talk about is the fiber to chip attach at scale. So today, most fiber attach still relies on an active alignment as powering the device, optimizing for PIC signal, and fixing it in place with epoxy. This requires submicron precision, and it's done one device at a time. This is slow, expensive, and incompatible with AI network volumes, and is specifically challenging for FAUs or fiber array units. The alignment and the UV cure time seems to be dominant here. So there are several techniques that are being developed and studied, and each of them has their own pros and cons. And what's still missing is really the high throughput passive alignment to guide the optical fibers into place without needing the device powered to find the signal. And there is a deeper issue here that nothing is standardized. Today's flows remain tightly coupled to foundry processes stack, foundry-specific optical I/O, and then custom recipes. So every foundry or process change triggers a new fiber attach development, and tooling, qualification, yield learning, also they don't transfer between the different players. So until the industry converges on a small number of reference flows, the cost reduction curve that AI infrastructure demands, it really won't materialize. The second gap emerges here as we move from pluggables to co-packaged and near-packaged optics. In order to achieve the required power efficiency and latency that photonics demands, this is now placed extremely close to high-power ASICs and GPUs. This is a very challenging thermal environment, as we all know. So one common response is to use external lasers and feed light in by fiber. That has clear benefits in thermal management and serviceability, but it's not the only viable architecture. Integrated laser, as we know, has implemented in a number of Nokia's products, offer higher reliability and enable use of lower power lasers or fewer high power lasers with reduced blast radius. And this is important considering that the laser shortage that the industry is facing. But there is a condition here that the laser should stay within their operating temperature window. So, like in my opinion, what is missing here is that we need a true system level co-design. Thermal, mechanical, optical, and electrical, they need to be engineered together rather than in isolation. So today, these are often handled in separate silos, and the final design reflects a set of compromises. And this is where the emerging substrate technologies such as glass interposers become very interesting. Unlike silicon, glass is a strong thermal insulator acting as a barrier between the hot ASIC and the temperature-sensitive photonics. It's also electrically insulating, which improves high-frequency signal integrity, and its coefficient of thermal expansion can be tuned, reducing mechanical stress and improving long-term reliability. So glass also supports advanced packaging features like ultra-fine line RDL and better optical waveguides and 3D integration. So it really opens up design space that conventional approaches cannot reach. There is a third gap as well, which is the test. And this is quite important. In electronics, the principle is very clear. We don't package a faulty die. So known good die or KGD is foundational. in photonics, that principle is not fully and efficiently realized yet. Also, we often don't know the full optical performance until late in the packaging. And wafer die level performance can be different from the package module. And this is because really the packaging itself, fiber attach, thermal mounting, and mechanical stress, they all shift the optical behavior. And that's a serious yield risk, specifically when photonic dies are co-packaged with expensive AI ASICs. That makes the problem even worse. So here, there are two problems that need action. So first of all, like the optical wafer level test requires sub-micron fiber alignment to couplers that cross hundreds of devices per wafer. Again, this is not efficient, this is slow, expensive, and doesn't scale. So we need automated optical probers, and the automation really has to extend into the test as much as into the assembly. And the second is that what's really missing is that the link between the foundry and the OSAT. We need a unified interface standard for optics and handoff protocol that contractually guarantees yield, reliability, and package performance. Just to summarize, and what we need to close the gaps that I just reviewed, we need three things to happen. So first, the industry needs to converge on the reference manufacturing flows, particularly for fiber attach and laser integration. So the tooling and yield learning can scale across different players. Second, we need true system level co-design of photonic packages with thermal, mechanical, optical, electrical considered from the start. And then the third is that we need to establish the KGD, or known good die for photonics, wafer level optical probing, test over design, and standardized methods that match the wafer level performance to package performance are essential. Yeah, thanks for your attention.
Thank you, Armagan. Really, really interesting talk. So a question from me. You discussed active alignment as being fundamentally too slow and expensive for future AI demands. How realistic do you think is fully passive high throughput alignment in the near term? And what still, in your view, needs to be solved? And I guess to add to it, are Nokia trying to solve that themselves, or are you relying on innovation from this community?
Of course, we rely on the innovation from the community because we don't work in that area. But really, it might be too good to be true at this point, having fully automated passive alignment. But this is really at the end what we need for this scale, because what we see today is that fiber alignment procedure, it takes, it's time consuming, and it does not scale. So that's very simple. So based on what we see today, so the time that it takes for us to power on everything to align and apply the epoxy UV curate. So this whole process is not is very prohibitive for larger scale manufacturing for AI demands. And this is what I wanted to ask the industry. I know there has been some work around it, but we really want to rely on the ecosystem partners to work on it and to enable that. That's gonna, in my opinion, make a very neat solution for today's demands that I'm sure most of the companies are dealing with it today.
Well, if you think you can enable that in the audience, then please write in the chat and we can connect you with Armagan. There's a question from Maves Yousefi from Photon First. What's on your mind?
Hi, thank you very much. So I'm sorry I forgot my anti-reflection coating, so it's still reflecting too much. Question would be that this is a very nice idea. Thank you for the talk. But you require a bunch of peripheral technologies like the automation equipment, etc., to come into play, to be mature in order for you to do this. Do you have an internal timeline, or do you know when we could expect this to happen?
So so the obvious answer is as soon as possible. But I think just catching up with the wave of the co-packaged optics and near packaged optics, we're looking into a timeline of 2027, 2028, really. So I think, yeah.
Okay, great. Well, thank you, Armagan, again. That's a great start to this conversation. Please stay in the room and contribute to the other talks. So next, I'm delighted to introduce Liron Gantz from NVIDIA, who works at the forefront of AI infrastructure and next-generation networking architectures. As Jose already said, Liron is one of the keynote speakers for our upcoming Global Advanced Manufacturing Alliance meeting taking place in Brussels. And today he'll share an NVIDIA perspective on the technologies and manufacturing innovations required to scale AI data center infrastructure for the next generation computing. Liron, please share your slides. The floor and the attention of everyone is yours. Thank you.
Sure. Thank you. Okay, can you see my slides?
Yes. Yes, perfect.
Okay, great. So thank you very much. I'm Liron Gantz from NVIDIA Research. And today I'll give a short overview of how AI data center scaling is driving new requirements for networking, photonics, and advanced packaging. So in many ways, photonics actually becomes synonymous to advanced packaging. It cannot scale without advanced packaging. And today, AI scaling is not just about, it's not that limited by the compute. We actually need to move insane amount of data from one point to the other. And that's driving a lot of innovation. And that's one of the bottlenecks in photonic scaling or AI scaling at all. So, sorry. Yeah. So when we talk about AI scaling, let's define 3 different domains. So the first domain is the scale up. And this was already mentioned in the last talk, but scale up is about connecting a few GPUs to act as one big GPU, to act as one super node. It usually defines, it usually uses a very high bandwidth connections. And at this point, we are still using copper for these kind of connections. The other domain is the scale out, where classical networking is being used. This is where co-packaged optics actually comes to play. And here we are connecting a few racks or across an entire data center. But there is actually a third domain, which is lately was introduced, but I think it's becoming more and more important. And it's becoming more and more important, and that is the scale across. And in the scale across, we are connecting a few data centers. As I'm saying, training does not stop at the rack. We want to utilize many data centers to enable training. So we need to use the networking that we have today to connect several data centers, and that brings a lot of new barriers. For example, latency. How much far is far enough? How far can we connect to data centers where latency does not kill us, or power does not limit or kill the link? So now that we have defined all of this, just for you to see, these are the scales that we are talking about. Scale out is moving at a stream scale, and you can see that the magnitude of these new data centers, and this is the reach that we have to get. One more thing is that optics today, as I mentioned, actually controls 2 of these domains, which is the scale out and the scale across. In the scale up, we are still using copper cables, but they are very, very limited in reach. So if we can make our optical links much more efficient, then at some point we can replace the scale-up network from using copper to using optics, and which will be kind of amazing if you think about it, because we'll have links, optic links from the scale of millimeters to the scale of kilometers, which is several orders of magnitude, and it's pretty amazing. So now we understood this, let's talk about what consideration we need in AI networking and what makes a link efficient. So let's start with throughput, because that is the most easy to understand. You've all seen how the data The data rate scales. People have mentioned Hyper-Moore law, or people sometimes call it the Jensen law. Every 18 months, it's order of magnitude more. So throughput is kind of obvious. But I want to raise awareness to something else that I found that people talk less about in our industry, and I want to explain why it's very, very important. And that is radix. And what is radix is actually the number of I/O per ASIC. How many connections we have from each switch. And why this is critical, because the higher the radix, the flatter the network. So I want to show you a very simple example. Let's say we have a switch with radix 2, which means it's only have 2 connections, and we have another switch with radix 4, which means it has 4 connections. So if I want to connect this node to this one, I need to do 1, 2, 3, 4 hops, and each hop is latency. So in this kind of network, I have a lot of latency. But if I have a larger radix and a flatter network, then I only need 2 hops in order to connect each node, which means less latency. But even more important, look at the number of switches I have here. I have only 1 switch. Here I have 3. So I saved number of switches. I saved power. I saved cost. So radix is very, very important, and radix directly connects to the number of fibers we can break out of the chip. So we need chips with a lot of I/Os, and that is a big challenge in the optical community at this point. But hopefully now you understand the importance of that. Other KPIs that are of course important are reach. As I mentioned, copper cables can reach only 3 meters. Optics can reach from millimeters to kilometers. Power efficiency, which I will mention in the next slide. Of course, latency, which we also addressed when I mentioned radix, and edge bandwidth density, which is directly influenced by packaging, because it defines how many available electrical and optical beachfront we have, and they also limit the radix. So let's look at the packaging. So today we are at the stage where we use COUPE on MCM, and when you consider COUPE is actually pretty amazing. It's 3D stacking. It's optics. It's 3D stacking of optics. But today we are limited by the number of bumps. And that makes the only way to scale in this kind of architecture with regard to rate. We can only increase the rate. So that's why we are talking about 400G in the next generation. And from packaging point of view, we need to introduce new kind of materials like TFLN or any other new material that can allow us to go to higher and higher rates. The other consideration is that when we go to higher rates, we need very, very strong SerDes. These are the devices that aggregate the data. And the more you aggregate the data, the more latency you have and the more power consumption you need. So you actually pay twice in this scheme. Hopefully, you want to get to a point where we can have something like COUPE on COS, which is an interposer. Then we increase the number of bumps, or increase the number of available channels that we can transmit the data, and then we can go to a more moderate rate, or at least the option of going to more moderate rate is open up to us, and that can save a lot of power. And again, we are shifting the demand from faster modulator or faster optics to more efficient optics, and that's a bit different, because when we have an efficient optics, when we have an efficient modulator, one that have a very low VPIL or a very high picometer per volt, we can actually do the thermal tuning with capacitive tuning and not resistive tuning. We can save a lot of power that way. So as I said, the shift can go from faster modulators to more efficient modulators. And of course, maybe the next stage is to go to a large-scale photonic interposer when we have an entire system that sits on the PIC, and we have much more channels to connect to the data, and we can even go to lower and lower data than in the previous generation. So with that, I want to summarize in one sentence, that is, packaging increasingly defines the achievable communication architecture. So when you enable us new ways, we can think of new architecture that can save more power, save latency, or reduce the latency, and be much more efficient. And with that, I'd like to thank you.
Thank you so much, Liron. Incredible progress, as always, from NVIDIA. I want to go straight to Stefan Heinemann from Fix. What's on your mind?
Thanks, Liron, for this fantastic presentation, really summarizing it very well. Do you have any kind of guideline for density requirements of the electrical and optical interconnects in that scenario that you showed? Are we down to the sub 10 micron into the micron level densities, or where do you see this going?
So we do have requirements, which I think we published in the past. I don't remember the numbers by heart, but I can refer you to the publication where it's specified.
Thank you.
And Liron, NVIDIA sits in, I think it's fair to say, a unique position across the ecosystem. Where do you think stronger collaboration is needed between foundries, packaging providers, optics companies, and system integrators?
I think all of them is very, very important. I know, and then this is kind of an answer that says nothing, but we really see that every stage of the way, every part is connected to the other. So and it's something I always say, that in the future we won't have analog designers that are responsible to the interface. We will have interface designers that are in charge of the optics, the electrics, the packaging. Everything is connected. And I think one of the most important things is, if I'm allowed to say, is that to enable software that can support this multi-disciplinary field.
Thank you. And we have a question in the chat from Taha Ayari, who wants to know a little bit more about the photonic interposer. Taha, could you unmute and ask your question?
Yes, thank you. So yeah, my question is about to give, if possible, more details about what you mean about photonic interposer. Is it a glass core substrate? Is it meant to integrate some waveguide structure in it? Or
so I left it vague on purpose, because any good solution that can route a lot of waveguide with low loss is a good solution. So I don't want to constrain you to say this is glass or silicon nitride. I want you to give the solutions to that. I want you to find, and if it's a new material that you discover, that is also fine.
Thank you.
And Liron, Armagan touched on this, and I know it's going to come up again today, but many of the industry still see fiber to chip interface as one of the biggest unresolved bottlenecks. It seems pretty fundamental. And how important is reducing that FAU complexity, such as the number of active alignment steps and coupling loss, to enable practical hyperscale deployment of co-packaged optics?
So I think that directly connects to what I said about radix, because this is one of the main issues. Having low loss, good connection that can also not limit us with regard to the number of fibers that we can take out is very, very important. That will define the architecture of the network, essentially.
Thank you. And there's a further question from Stevie Codette in the chat. Stevie, could you ask your question?
Thank you for the presentation. Yes, my question is related to the latency. You mentioned that this is a key point, and I would like to know what is the target latency you're looking for in the case of the scale up, scale out, and scale across that you showed at the beginning?
It really depends on the application. So it's a different latency for training, and it's a different latency for inference. So for example, you don't want the inference to have a large latency, because then you will be waiting a long time for the answer. But in training, maybe you can tolerate higher latency if you do the training correctly, if you can divide the training or for different agents. So it's really depends on what is the application you are targeting.
Thank you.
Okay, great. Well, thank you, Liron. And next, I'm pleased to introduce Sandeep Sane, Senior Director and Head of Packaging at Lightmatter, a company at the forefront of photonics-enabled AI infrastructure and optical interconnect technology. Today, Sandeep will share Lightmatter's perspective on how advanced packaging and photonics can help address the growing bandwidth, power, and scalability challenges facing next-generation AI data centers and high-performance computing systems. Sandeep, you've shared your slides. The floor and the attention of everyone is yours. Thank you. Sandeep, are you on mute, possibly?
Now I
muted.
I was on mute. Let me share. Everything coming through well, John?
Perfect. Yes. Thank you.
All right. So thank you for inviting me here. And what Liron and Armagan has said is really puts my presentation in the right perspective. You will sound that we are all saying similar things. So which actually tells that for the industry, what are the big challenges? And we are all cohesively saying similar challenges that we are seeing to how we will, what is needed to bring this technology into high volume. Right? So if you look at we all know the copper has some limitations, and we all talked about it. So if you now look at the promise of silicon photonics, this is the way we see the problem, how we evolve silicon photonics technology, going from pluggables, which is what we call in the current generation, where you're getting energy efficiency anywhere between 7 to 20 picojoules per bit. And just for scaling, we are calling that as 1x bandwidth. As you move the silicon photonics devices closer to ASICs, say near package optics, you gain efficiency and also you gain bandwidth. And further, if you move to the generation 3, where you now integrate these devices onto the package itself, what we call 2D CPO, you're further increasing the bandwidth from up to 10x. But really, where the value really starts becoming very clear is if I get into the 3D CPO photonic space, as well as interposers. Somebody asked a question before about optical interposers. We are absolutely working on that concept, and we already have some products out there, reference designs out there. And when you go into the 3D space or interposer space, this is where you really now scale the energy down to 2 picojoules or around that. And then your overall bandwidth against the pluggable space is almost 100x. So from Lightmatter point of view, we are really looking at this entire roadmap and solving the problems as is evolving and the demand of the silicon photonics is evolving in the industry. Just to tell you where we are today, this is just where showing from a link performance. We have already demonstrated some of these links, 56 gig NRZ up to 16 lambdas per fiber, 112 PAM4 up to 16 lambdas per fiber, and now we are also working on 224 up to 4 lambdas per fiber. Essentially, these are all in silicon in our labs today. We are showing that we can deliver 800 to 1.0 terabit per fiber that is available today. And it can support both bi-die, uni-die up to 32T per optical engine, and you can support up to 1 kilometers. Right? And we are both standards or custom design as needed. But beyond from a technology point of view, we are all focused on, while we deliver what is needed for the market, but we are heavily focused on what we can bring as a key technology enablers with the 3D CP or interposer programs. And these are the two activities that we are heavily involved. The first one on the left shows a 3D CPO, what we call our L series. This is all based on chip on wafer assembly flows, where your EIC die is attached on the PIC die as shown, and it's 3D integrated. with detachable fibers at the perimeter. As Leron said, fiber attach and giving the radix that customer wants is a very critical vector. And we believe that detachability allows you to do at least solving a fiber attach problem. And the next question is, how can you scale? How many fibers can you really attach per edge, which is a scaling problem that we have to focus on. But by doing so, we can really deliver on the CPO front, on the 3D CPO front, we can deliver a CPO engine up to 64 terabits bandwidth. The one on the right is really the the optical interposer, what we talk about. And we have this, what we call as M series. Again, you can see all the chiplets on top. These are all the EIC chiplets that are sitting on top of a photonic multi-reticle interposer. These are retically stitched optically. And this is again built on a standard chip on wafer assembly flows that are fairly prevalent in the mainstream advanced packaging technologies. By doing so, this is a reference design that we have demonstrated that we can support up to 114 terabits on almost a 2000 millimeter square die complexes. So this is what we are really focusing on bringing some of these technologies into the market. Now, if you look at what are the key challenges for us to enable some of these parts to high volume, and it will sound very similar to what Armagan has said, which is very good to hear. There's the same voice coming across, right? And I'll go through 4 challenges that I see from my point of view, very similar to what previously talked about. Number 1, delivering a known good optical engine is a must-have, right? And there are different packaging technologies here to showcase. First one is a standard package where you have an XPU die complex sitting on a standard substrate connected to optical engine. The die-to-die routing between the XPU to the optical engine is on a standard organic substrate. Fairly straightforward to integrate this. But quickly, we'll have, because your electrical bandwidth is going to be limited if I continue to be on a standard organic substrate, you will have to integrate optical engines on advanced packaging technologies. And there are some of the technologies are EMIB style technology that Intel has, which is fairly easy to integrate, I would say. But then there are other technologies like CoWoS or CoWoS-L, where now you need to dedicate the optical engine to the die complex upfront. And this makes it very critical to ensure that when we build the optical engine, it's a known good to ship it out to any end customer. Think about it like almost like an HBM. HBM people build it and they ship it out. Optical engine needs to be very similar approach. The second is, how do you deliver scalable fiber attach solutions? And this is where we have gone through multiple attach schemes. And what we believe is, when you look at what is feasible, if you look at the key performance indicator for high volume manufacturing, those are the metrics shown on the table. We believe that shifting left to the wafer scale optical coupler attach is very critical. By doing so, by attaching these optical couplers and making this detachable as a part of the solution, you can really test out the PIC interfaces very cleanly before you commit an expensive EIC die on top, as well as when you look at the EIC PIC stack, you can test the whole stack before you ship it out to any end customer. If I do other traditional optical attach, fiber attach methods such as V-groove, this is not possible. So moving to a wafer scale processes is very critical. And we have done some announcements. If you go to OFC, we have done some of the big announcements as from Light Matter on how we are solving these challenges. The second piece is, of course, the cost of these FAUs. Cost is a big deal here, right? One of the FAU is one of the main BOM costs, and it is primarily because of the manufacturing. It's manually done, and it's driven by the PM fibers, because the requirement of the rotation of the stress rods, that really is very time consuming. So industry needs to think about how do you automate that? How do you bring the cost down for some of these connectors and make this standardization is a must have. The third challenge is delivering to scale on HBM is really equipment and materials, right? Equipment, you have to transition automated alignment in seconds, not in minutes. You have to be able to do parallel processing so that you can handle alignment, dispense, and UV cure in parallel. And also, we should be able to reconfigure these equipments to support multiple products. From a materials point of view, this is the biggest time adder today. Epoxy, if we can have an ideally epoxy, just to showcase this, right? We are showing how many epoxies are used in a simple wafer level attach process, and you will see at least 2 or 3 epoxies are used. If we can align to one single epoxy, that will be ideal. It has to be reflow compatible. Fast UV cure, less than 5 seconds would be ideal. Today, this is the slowest step in the flow. It takes tens of seconds to minutes. And of course, lower TG would be helpful to conform to different warpage requirements of these devices. And the last one is really cost, the total back-end cost. And people are not used to these numbers. If you come from a traditional market, semiconductor technology, if you look at the PAT, package assembly test costs, in the silicon photonics world, just as a demonstration, it's shown that package assembly test cost is almost 60 to 70% of the total cost. Traditional market, it is somewhere between 25 to 30%. So this is a big thing for everybody to understand that, oh, package can cost so much. And if you look at reasons for it, is fiber attach is one of the key things, but higher test times and lack of standardization, similar to what Armagan has talked about, is really causing some of these costs to be much higher. So while we ask the test vendors and all to work with us on solving some of these problems, but from an product architecture point of view, you really have to design products for DFT, DFM, which is a standard practice in the mainstream industry. But in silicon photonics world, this has to come upfront and really drive the equipment and material development to really push the throughput higher through assembly and test. So with that, thank you for giving me time to express my opinion, and I'll be open to any questions.
Thank you very much for coming and express your opinion. You know how much we love light matter at Optica, so I would like to start by saying that thank you very much for everything that you are doing for the organization. There are many questions in the room, but I would like to start. If we could help you, we have 187 people in the room who wants to help you. What would be the biggest headache, the biggest challenge that you would like the room to help you with?
If I were to pick, means when I look at the 4 challenges that I've listed down, I would really focus on making wafer level fiber attach a primary way to solve this issue. And with that, if you just take that problem statement, this has every aspect of it, like fiber attach, materials, equipment, how do you bring that all together to solve that problem? What we bring to the table is really the test chips, and we have our own expertise, but we would really love to collaborate to see how we bring the entire ecosystem so that we can solve this in a meaningful
Sandeep, just one thing. Wafer level fiber attach, can you give me like a number that would make you happy in terms of insertion losses, fiber to chip?
Oh, insertion losses, it has to be less than 1.5 dB. I think this is the classical issue, right? If you give the overall link, if you ask a photonics engineer, they will say, give me less than 1 dB. But if you put realistic manufacturing hat on your hat, I think 1.5 dB is achievable, and that's what we need to demonstrate in high volume.
Right now in the chat, anybody who can achieve less than 1.5 dB insertion losses, wafer to fiber, please write so in the chat. We have questions in the room. The first one is coming from Photon First in the Netherlands. Mirvais Giuseppe, what's on your mind?
Hi, thank you. What a nice talk. Very, very interesting. I'm going to ask the same question I asked Nokia, because the key enabler for you to reach these targets is the automation partners. They have to be able to help you to bring this to the field. Let me ask your opinion again here. What do you think is the timeline for them to match your roadmap?
I think I would agree with Armagan. We need these equipments by 2027-28 timeframe. And these equipments are high precision and high throughput. That's what we need. Right? Because if you do a wafer level, and if I do a lens attach on a wafer level, depending on the size of how many lenses I'm attaching, that's huge amount of time it takes per wafer. So automating precise alignment, automation, parallel handling is absolutely must.
Sandeep, you were very clear the 1.5 dB. You're thinking about fiber to wafer. Is there a need for fiber bundles? And also give us a list. How many fibers at the same time?
Oh, so this goes to what Leron has said. It is all about radix, right? In general, the roadmap, we look at it. Today, we look at, if I look at a shoreline, take a pick, 33 millimeters is a shoreline on the full reticle. Maybe today we are about 100, 110 fibers on that edge. But the demand is to double it every generation. So in general, we'll have to double that to 200 to 300 millimeter fibers on that edge. So you can imagine how much fiber per millimeter you'll need as you scale. Right? And that technology is very complex on how do you align, how do you manage that whole in the real production environment.
Sandeep, please stay with us because we're going to have a couple of very interesting companies that want to ask you things, but I want them to ask when they're giving the short presentation. But now, Sandeep, if we are thinking about the scaling up, and I know you're working with all the OSATs in the world, I would like to bring to the table one of the ones that is making a big impact in the whole manufacturing of transceivers and CPO modules in the world. I'm talking, of course, about one of the largest companies in Optica, Jabil. Thank you very much, Greg May, from being with us today. Tell us how you can help us, but most important, how the 185 people in the room can help you. The floor is yours.
Hey, hi, can you hear me all right?
Loud and clear.
Okay, perfect. Just one moment, please. Okay, just going to share my charts. Okay, hopefully you can see my charts now.
Yes, we can.
Okay, so thank you for the lead up, and actually and I hope you're seeing the right one. You're not seeing the preview. You're seeing the proper slideshow.
We need to do a display settings change.
Yes, yeah.
We are
okay,
seeing
we had
your
that problem
side
earlier. Okay, here we go. You know, I think my positioning in the presentations is great because the previous speakers have teed up quite a number of problems that are very familiar to us at Jabil. Also, Jabil is unique because not only are we a manufacturer, a contract manufacturer, so we are capable of making most of the products that have been described earlier. We have our own products as well. So we share your pain. We understand a lot of the problem statements that have been brought up so far. So Jabil, So Jabil, just to flash up what we are, is a $30 billion global behemoth manufacturing all over the world. We are in the intelligent infrastructure business unit. So out of the 30 billion that we revenue last year, intelligent infrastructure was 3.7, and thanks to AI, as we were all seeing, it's grew at 34% last year. So it is giving us numbers, giving us quite substantial issues with scaling up. So what Jabil does is we're not involved in designing the PIC or fabricating wafers. We take the wafers in at the head end of our process. So we have wafer level processing for silicon photonic, both 12-inch and 8-inch. And from there, we can take in, we can do the testing function, we can back grind, we have dicing. So, we can move from there to flip chip, the fiber or lens attach processes, lid attach, and further functional testing. The nice part of this is that it can be all under one roof. So there's no need to manufacture by FedEx or to ship product around the world to get it processed. We can do that within one roof. And then going forward from there, and more of our traditional business, we can put those optical engines or whatever photonic parts onto circuit boards and also do the electromechanical assembly. Okay, so that's all within Jabil's remit. The photonics area is just over 10 years old, but growing very rapidly. Okay, most of the audience knows this already. So some of the applications we deal with are transceivers. We manufacture products for other, we have many customers that we make transceivers for, but we also have our own product line. from the acquiring the Intel product line about 3 years ago. So we have our own going out. We're involved with co-packaged optics and products in that realm, quantum and LiDAR. So some of the applications that were discussed earlier. Those of us who have been in the industry long enough remember the dot-com boom of the late 90s and how crazy that got and the kind of challenges it portrayed. Now we're in .ai. So basically we're back seeing it again, but this time with a lot more, I would say a lot more vigor and a lot more investment, a lot of real money in this. So a very exciting business for us if we can keep up. So the hard part is actually keeping up the demand that's going out there. I won't dwell too much on this. We recognize and acknowledge a lot of the packaging schemes that were presented earlier. This is a overly simplified view of that. And fiber attach, we also recognize that. So we have been involved with fiber attach for a very long time now, relatively speaking, starting with single fiber and coherent type of applications. But now we're getting into fiber array units and parallel fibers. There's a number of schemes for that, as we all know. So there's edge coupling, but there's also V-groove. We are seeing active and also passive. I think with the passive, there's a simplification that comes in without having to power the unit, without having to calibrate detectors, without having to do a lot of the overhead. But when it comes to actually manipulating the fiber array and bringing it into position and then curing, also can be quite lengthy even with passive alignment. So we do have a big challenge here and a big capacity bottleneck when it comes to alignment. For some of the volumes that we're seeing, we're getting many alignment machines required to keep up with it if we don't find a way to break the mold and come up with a different way. So Jabil's core competency is volume manufacturing. So we really do understand what it takes to get something out the door in high volume consistently. And something with like photonic advanced packaging, yield is a real potential issue because you're dealing with so many different adhesives and different manual steps. Adhesives are actually quite challenging to manage, everything from expiry date to supply chain to how they're handled, how they're stored. Automation is critically important, but in photonic packaging, it runs contrary because loads and unloading especially are quite difficult to do automated fashion. So there can be, if you're not careful, have a lot of manual manipulation. I don't think we spend enough time really thinking about all the materials that go into advanced packaging to make a robust product. And it can take a number of iterations and experiments to actually figure out exactly what you want to do there and to meet the robustness as well as the manufacturing volume objective. We see this with work instructions, the workforces that we need. We're in big scale up. You don't have time to train a big workforce. You don't have time to deal with churn in the workforce. So you have to have very clear instructions to your operations personnel. And then finally, as mentioned previously by some others, production test is really important and catching it at this earliest point of value add. So getting your production test to detect a build error or a defect early before you start adding in expensive parts like DSPs, lasers, and other parts like that. So the bottlenecks kind of run in parallel with the volume. So the message here is to really, you don't have a lot of time, but the time that you have should really be spent in high quality figuring out your prototype and your pilot product. So spend the time, invest the time and energy to get that right, and that will pay dividends in the future. If you don't do that, you're going to proliferate problems into your mass production and end up with a lot of yield issues. Okay, so the approach that we do here with Jabil is that we take a DFM, DFT philosophy. And what we've done, I think, which is fairly unique in the industry, is that here in Ottawa, we have an NPI environment with a lot of the same machines that you would see in a volume environment. Okay, so we have our fiber attach, we have die bonder, we have pick and place, we have reflow, in a captive NPI facility. So this gives you the time to do your experimentation without interfering and competing with mass production in an environment that where you're surrounded by subject matter experts. And what we've been finding is that if we work very closely with the customers, but also with quality assurance labs, so rapid turnaround of imaging and sectioning in particular, is very important to drive and iterate to a robust solution. You know, once you have to figure out things like your temperature profiles to get the integrity of your solder correct, make sure it's void free. We in Ottawa have a fluxless reflow system. So instead of using chemical flux, we use a formic acid vapor that reduces residue and allows keeps the voiding out of underfill, and also produces clean photonic parts that are that are less obstructed with particles when it comes to align and attach. So we work closely with our customers. We apply, I think you'd recognize as similar to Six Sigma. We work collaboratively with the design. We improve, we measure the outcome, and we circle back. So as we iterate to improve. And the whole goal is to get what we know very well from other industries, is to get a lineup with build documentation, bill of materials, work instructions, everything, test methods that actually pinpoint where the source of the problem is, get all that out of the way, and then phase it into the volume factory. I think if you don't get these, if you don't plant the right seeds, you don't get the right result at the end. So we've really embraced that concept. And then finally, just a bit about what we do. So here in Ottawa, we have a advanced packaging facility, again, a captive NPI facility with a lot of the processes that you would recognize. I won't get into the detail there. And then currently in Jabil, even though the corporation has probably hundreds of factories, the one that we deal with most is in Malaysia, but we are currently bringing up factories in India and the US as well. Okay, that's my presentation. Thank you.
Thank you very much, Greg. Thank you for being here. We keep receiving fantastic, amazing feedback from all the different big companies that collaborate with Jabil. Is it limited to big companies when it comes to Jabil? Because most of your customers, at least the ones that I know, they are typically large companies. But I think your presentation today said a bit otherwise.
No, absolutely. We, especially in the NPI facility, we will work with just about anybody. There is a hook there, though. We're not like, there are lots of research institutes that will help you develop packaging, but they're disconnected from the mass production. You can get it through the research institute, but our philosophy is to be a gateway to mass production. So the little guys we work with are the ones that we think can get into the factory next, that have really high potential for volume.
We have a lot of questions for you. I'm going to address them quickly. The first one is coming all the way from the masters and commanders of microtransfer printing, Exceloprint. Dan Pitt, what's on your mind?
So the question I asked in the chat was, Jabil has an amazing portfolio of capabilities, all the way from, design, wafer, fabrication, packaging. And we're looking today at these real challenges in packaging and integration. And the question I posed was, where does Jabil intend to lead? Where do you want to really,
interesting.
Yeah, be the one we look to for solving these problems we're all talking about?
Well,
you seem to have the skills.
There's two prongs to that. We want to lead in the assembly methods and manufacturing methods. That's our we're not going to be the people that are going to come up with the next, or the RDL, or the through silicon via and the 3D, the best way to do 3D, for example. We're going to be the guys that we want to lead on the best practices for adhesives, kind of almost the boring stuff, the adhesives, the solders, the curing, the handling, the reliability behind that, the quality behind that. That makes sense.
What do you think about the previous presenter's discussion about trying to find a single epoxy for all optical engines.
Well, I think that would be the silver bullet, right? If we could find that, if there were such a thing. No, I'm not the technical expert on that, so maybe there is hope for that. But if you had a very fast cure, like the ultimate would be a very fast cure, non-shrink, robust epoxy, that robust against damp heat, shock, vibration. You would have a major advantage if you had something like that.
If anyone has a fast cure, no shrink epoxy, please write so in the
Fast
chat.
cure,
Thank you very much,
no
Dan.
shrink, damp heat resistant, shock resistant.
Thank you, Greg.
There is another
No
question
problem.
for you, Dan. Stay with us because you are speaking next. But Greg, there is a question coming all the way from the Netherlands. Jorn from Epiphany. What's on your mind?
Yes, thanks a lot. So you said you're already handling with small companies where you believe, right, they actually can scale up. And that's important time to market, that we don't need to have to redesign. So how do we design in order to seamlessly go to manufacturing?
Early engagement.
And how do we engage?
Well, that's a good one. It's always a challenge, right? I think you approach. I think the gateway in Jabil would be our salespeople, just to get known to them. They're the ones that do the conferences and are always out with the customers. Get involved with them and see if we can start an early engagement like your concept, and then see where we can help on DFM. You really have to nail DFM and DFT early on.
Yeah, 100%. That's why I'm asking.
Yeah. No, it's. I don't know. I wish I had a better answer for you, but I think that's the best way. Like, there is a lot of activity in the marketplace. We do get approached by a lot of people.
One more question coming all the way from India. There's a new startup there called Qualigon. They do silicon photonic gas sensors. What is on your mind, Sandeep?
Hi, Greg. Can you hear me?
Hi.
Loud and clear.
Yep.
Yeah, perfect. So we are basically designing the PICs for gas sensing applications. So we succeeded in designing passive and active photonic ICs. But one of the challenges that we are facing from the last 2 years is how do we package the systems? Because everywhere we go, we found the packaging for telecom or datacom. But when it comes to gas sensing, because it requires inlets, outlets, and flow rate management, pressure management, all this becomes very much challenging in terms of, PICs for sensing application. I think I just got a reply from Photon first, but yeah, just want to hear from your end as well. Thank you.
Yeah, I don't think that we would provide a design service for that. That's quite a unique application that would have some very interesting like considerations for flow, for example. That's not, I would say, a core competency of ours. We would be more able to help you with making the mechanical part, like molding, material choices, things like that, any kind of machining, any kind of assembly of that. So I think you need to find a third party that can help you with the unique part of your application.
Sandeep, there are many people in the room, but apparently one of them already reached out to you that they can really help you on this. And
yes,
now we go to the masters and commanders on microtransfer printing again. Dan, please tell us shortly what you can do for others and others can do for you.
Well, what I can do is introduce our CEO, Peter Smith, who will give the presentation.
I did not see Peter. Great to see you, Peter.
So Accelerprint has been around for, I don't know, 13 or 14
Peter
years.
has one slide to share with us.
Yeah.
So I'll hand it over to Peter.
Can you see my slides?
Not yet.
Not yet.
Okay, just let me share here. Should be coming through loud and clear and up on the screen now.
I see it's loading. There it is.
Okay, great. Thank you very much, Jose, John. It's great to be here. So I'll give you a very quick run through on microtransfer printing technology and where Accelerprint is today in providing manufacturing solutions using MTP. So microtransfer print is an incredibly versatile heterogeneous integration mechanism, and it's being deployed right now, addressing the major concerns of key industries that we've all been talking about now, primarily high performance computing, AI, photonics, communications. When we say that it's a very diverse integration mechanism. What we mean by that is that we're not just talking about integration of devices like lasers and photodetectors, but also other materials, lithium niobate, for example, and even passive optics. So you can have many, many source wafers being transferred and integrated onto target wafers using the platform. And that's incredibly powerful when you consider all of the 3D integration challenges that the industries are facing today. So what are the advantages? The key aspect of all of this is placement accuracy. So very tight pitch, but maintaining precision while transferring thousands and thousands of devices. So we're well submicron currently at around 300 nanometers today, but with research partners, for example, with Tyndall, we're looking at sub 100 nanometer and hoping to advance that to a production stage later. Placement accuracy at volume is a key differentiator here that provides you with high density, of course, but also precision delivers low parasitics, which what you benefit there from, of course, is you maintain the performance of the devices that are being printed and the target application. It's incredibly important from a precision perspective to achieve that. And it also, that placement accuracy has the additional benefit of ensuring that you have low losses, improved thermal profile performance, and that in turn producing higher reliability. Another major benefit of the platform is in reduced material usage. So when you're using MTP with incredibly expensive wafers in photonics, for example, MTP has the advantage that essentially you're removing the device layer, which leaves you the expensive source material wafer for recycling and reuse, which of course is incredibly important for meeting the cost metrics that everybody wants to achieve with integration challenges. And critically, this is all scalable for high yield and high margin. So you have a solution now which delivers on all of the performance requirements, but can meet the really, really stringent margin and pricing required by these applications. And it's supported by a growing network of supply chain partners. It's been discussed already about end-to-end, how really important it is that the supply chain is connected for these applications. So microtransfer print with Acceloprint will deliver on that as well. So just to give you an example of a current example of very high volume production here, we're proud to say that we've been a technology partner with Seagate for a long time in this area. And Seagate have actually become a leading integrator of lasers, which is not what you might expect necessarily when we're all talking about high-speed comms. But they have been an early adopter in the use of lasers and in the dense integration of lasers in a very, very challenging application in hard disk drive with all of the yield and reliability challenges that hard drive faces for hyperscalers. What you're looking at is a capability of printing millions and millions of lasers with all of the benefits that you need in a very, very tough application. So very, very quick run through. Love to hear from everybody directly in the questions on the chat. Also just reach out directly to us. We have print centers operational in the US, Europe, and in Asia, and able to take on a lot of the applications that are driving the business in comms, particularly at this point.
Great. Thank you so much, Peter and Dan. So the Seagate hammer example you just showed was a really powerful demonstration of industrial scale deployment. How important was that milestone for Acceloprint in proving that microtransfer printing could move beyond research into high volume manufacturing?
Yeah, it's been a journey, but probably the best kept secret for quite a while, right? Because it's not simply that it's happened this year that Seagate is leading the charge in this type of integration. It's actually been happening for quite a while. albeit secretly. It's an important proof point, but it's not unique in that many of our comms customers now are beginning to see those benefits. So it has moved, you could say 2 years ago, really into a high volume production environment. And now the telecom and datacom sector is actually benefiting from the proof points that were delivered actually by hard disk drive. Even though it sounds like a different application, the challenges are exactly the same. Whether it's with or without adhesive integration, the diversity of materials that have to be handled, we passed way beyond research now into high volume production, and it's all on the same tool platform. So the tools that are in use for research and proof of concept are now moving all the way through to the volume manufacturing scale.
Thanks, Peter. And there's a question in the chat, Mavais Yousefi from Photon First. What's on your mind?
Hi. It seems to be the usual suspect here. Mavais Yousefi again. What's your strategy for non-good dies? Because you're implanting dies inside a larger wafer. The non-good die strategy is key to success in packaging. Do you do pre-testing? Do you do wafer directly, or do you do tested dies from a gel pack? Just for curiosity.
So it's application dependent, but we work with our customers to produce the source wafers with the expectation actually that we're getting source wafers with known good die available for printing. So in the early stages, working with our source material providers, we'll be making sure actually that when we're getting source wafers, we're in a position to identify no-gun die and print them accordingly.
Okay, well, thank you so much, Peter. Next up, I'd like to introduce Stefan Heinemann, Managing Director, USA and VP of Sales at Fix Photonics Assembly. With more than 30 years experience across photonics, lasers and advanced manufacturing, Stefan helps lead Fix's work on scalable packaging and assembly. Stefan, the floor is yours. Thank you.
Thank you, Jan, for the great introduction. Appreciate it. You can hopefully see my screen.
Yes.
All right. So yeah, what are we? Fix Photonics Assembly is a startup company, or is an established packaging foundry for integrated photonic circuits and also MEMS. And we are based in the Netherlands and also have United States facility. So what do? We support all PIC platforms, whether it's silicon photonics, indium phosphide, lithium niobate, you name it, that cover the wavelength range from UV to C-band. While we play a lot in the datacom industry, we are also very heavily engaged in quantum and sensing applications. We take it from prototype to volume. We actually, we heard from Jabel a very great presentation. We do digital twins and not only design the product, but we also do digital twin assembly. We bring it all the way from designing your product, DFM, DFT, all the way to the digital assembly line. And we have world-leading expertise in integrating a lot of different material systems together, active, passive integration, just in one dimension or in 2.5 dimensions. And when we talk about advanced volume packaging, what do we do in terms of scaling product? As you can, we address all these pain points or to a different level that you heard before from the end users. Fast, reliable wafer level processing of tested components of known good dies. And the core expertise is summarized here. Two different streams of the core expertise. One is wafer level assembly processes that are of active and passive, whether it's an optic or whether it's a VCSEL or a gain medium or a photodiode or another material system. We put die on wafer in a fully automated way with an accuracy of 300 nanometers and below. And then that's the process capabilities that we offer today on machines such as the Micro Nano. We have several of those on our floor, and we're actually running off processes that have been developed at IMEC and other research institutes, and we make them ready for taking it in at the Jables and the OSATs, big OSATs of the world. We're also addressing other issues that, what are other means for cost reduction in manufacturing, and that's shown in the lower one, where we go from individual hermetic gold box manufacturing to flow line lead frame assembly with semi-hermetic packaging around. And last but not least, just wanted to round up our presentation with one of our sample projects in the datacom industry, where we do attaches, fiber attaches in a fully automated way for the different configurations that are out there, whether it's a V-groove or an edge attach. And you see typical process capabilities of these different two mainstreams. V-groove is a very established process that is fully passive, gives you less than 1 dB insertion loss per facet. And Jose posted the question, hey, if you have less than 1.5 dB, please raise your hand. Here we are. We have that. We run that in semi-high volume production environment with very good process capabilities, whether it's a V-groove. The challenge that we have for V-groove is that they need special low index glues, and we heard a lot about epoxies. If you go to edge attach, insertion losses are a little higher. Process capabilities are yet still a little lower, and that is part of known good die strategy. What do we see in the future for us to address? And this is nothing new. We heard that from other speakers as well. Lower losses is always good. Better known good dies designed for test and faster curing, but also reflow compatible epoxies. So we're heavily investing in epoxy-free interfaces. Not only for that purpose, but also since we're pushing into the visible and the UV in many other applications, we need epoxy for interfaces. To the point of FAU supply chain, the attach process itself is probably not the bottleneck, the cost driver. It really is the single mode PM mode fiber array that also was mentioned by Lightmatter in that talk of arranging PM fibers in an array in a fully automated way to minimize cost. Thank you very much.
Thank you, Stefan. Great work as always from PICs. I see numbers less than 1.5 dB there, which is fantastic, which meets the spec. I see fairly large error bars there. Can you comment on, how repeatable the process is?
Yeah, and absolutely, and there's always outliers, and this is a summary of when we start with processes all the way through the different stages of the process development process. Outliers are there in the beginning, and the boxes, basically the color boxes, are where we end. And so you see the progress as we go through the different phases of our development processes with our partners.
Thanks, Stefan. In the interest of time, I'm going to move on, and I'd like to introduce John Anderson, Chief Commercial Officer of Photon Bridge. John, please share a slide and tell us how your work is addressing one of the industry's key challenges, how to efficiently integrate laser sources into photonic platforms.
Well, hello, everyone. Good afternoon. Thanks, Jose and John, for the invitation to come share what we're doing at Photon Bridge today, and really enjoying the opportunity to follow the great slides that preceded my short presentation and help set the stage. So, packaging lasers and how heterogeneous integration unlocks DWDM power for CPO. I actually think listening to the presentations that preceded, maybe there's a different subtitle. I really enjoyed the presentation from Lightmatter and the comment about we need to move from taking minutes to align photonics interfaces over different materials to seconds. So perhaps an alternative subtitle reflecting on this is how to solve that problem, how to move photonic alignment from minutes to seconds in packaging. That's really what we do and where the Photon Bridge platform shines. Let me find my mouse so I can go to the next slide. Perhaps don't need to spend too much time on this slide. I think the NVIDIA presentation probably addressed a lot of this already, which is great. But in line with what we hear from across the industry, data centers in AI are going to be moved to, in principle, by 2028, scale-up optics, and it's going to be slow wide, multicolored, lots of lasers. The big challenge for the industry, from a packaging perspective as we see it, is how do you package first 8 lasers, then 16 lasers, then 32 lasers, because that's the way it needs to go to meet the ever-expanding bandwidth requirements in a way that's actually manufacturable at volume and packageable at the right optical output power. And the optical output power is really important because that drives the performance of the system. How many CPO engines can you power, and what's the link budget and the speed and bandwidth of that CPO engine? And this is where we believe and hope Photon Bridge will have a role. Photon Bridge is all about bridging between materials. We have a platform that's built for laser packaging. Hopefully you can see the video that's playing on the right-hand side. You can see a placement of a laser or a modulator or whatever active device you like onto a piece of silicon. And it's all about single-step optical and electrical bonding in one go. We do in seconds full passive alignment to less than 200 nanometers based on a flip chip placement accuracy of 2 micron. That means you can do it at speed. 200 nanometer or less optical alignment, 2 micron placement accuracy at speed, fully passively. Our platform includes thick film waveguides, which means you can deliver and transport high optical powers, and you can be on wavelength. Basically, thick film for us means low process sensitivity, which makes the design and the performance of the MUX just better. And all this adds up to a manufacturable laser attach platform. Highly scalable standard flip chip tools, eye-line type lithography, so no exotic processes required. So what I thought I'd do next is share a little bit of an insight into what we're doing with this platform. This is the Photon Bridge laser source designed to scale. Picture of our TOSA, actually, that we've announced we are packaging with FIX, so great to also see FIX on this presentation. It's got on-silicon wavelength multiplexing, it's building on our high on-silicon power, it's scaling colors by addition, not amplification, which means you can move through 8, 16, and then 32 colors. And perhaps really important today, we bond fully manufactured burnt-in tested indium phosphide dye. Our process means that we have a path to multiple qualified sources. So that offers supply chain redundancy and resilience that we think is unique to the platform. We're developing it today. Stay tuned. Target performance is greater than 30 milliwatts per wavelength per fiber and targeting a 16% wall plug efficiency, which is what we believe the market needs today. If you're working on CPO integration or advanced packaging, we'd love to talk to you. Thank you again for taking the time to listen. I really love to hear questions, but if you'd like to reach out, these are my coordinates, let's say.
Thank you very much, John. And indeed, there are many people in the room working on this, but one of them is really working on this. Liron Gantz from NVIDIA, when you see that they can do 0.2 micrometer passive alignment, is this magic? What's on your mind?
So what I would like to know is, do you see a limit to the number of lasers you can package? So where will you draw the line? 36, 72? Can you reach more than that?
I think from the bonding performance, no, there's no limit. I think the challenge is really then become thermal management and packaging those and managing them all together. So yeah, we don't know what the limit is today. We feel very comfortable and we're designing 8 colors today and we see a clear path towards 16 and 32. Do we think it scales beyond that? Potentially, but we'd have to dig deeper to find that boundary.
Okay, thank you. Thank you very much. Very interesting.
Very well, thank you so much, John. Let's move on to Travis Scott, Senior Product Manager, Advanced Packaging Systems at Finetech. Travis, please share your slides and tell us how Finetech are enabling reliable, scalable hybrid integration and packaging process that can move photonics from R&D environments towards repeatable, high-volume manufacturing. I see your slides, but I don't hear you, Travis. I believe you might be on mute.
Hey, can you hear me now?
I can.
Rookie mistake. Sorry about that. Good morning. Thank you, Optica, for giving us the space and for curating a really great presentation today. So at Finetech, we manufacture die bonding and die assembly equipment. This is currently qualified at 0.3 micron at 3 sigma. We're trying to push this down to below 200 nanometers as well. We offer a prototype to production platform strategy. So you could start with a manual tabletop bonder for your R&D, and then you could go all the way up to automated production. The platform itself is a very accurate pick and place machine at its core functionality, and then on top of this, we can put on a various different array of modules. This covers all types of different bonding technologies, from thermo-ultrasonic, ultraviolet, and adhesive curing, eutactic bonding for laser assembly. And then on top of this, Fintech has 30 years of experience in providing solutions as a service. So we don't just sell machines, we don't just sell tooling, we don't just sell modules. We help you put these things together and to bring your products and prototypes to life. I'd like to get a head start on Jose and John's question of what we can do and what you can do for us. So what we can do for you is provide an extremely highly accurate and modular bonding system for your R&D and prototype and production needs. But what we would very much like from the industry is we're busy building up our next platform or our next system to cover the next 5 to 10 years of the industry requirements. And what we're looking for is partners from the industry to tell us exactly what you need from a die bonding and die packaging or like advanced packaging system. So today I've already made quite some notes. It's been a very interesting discussion. Thank you very much for the input of all the speakers so far. But if anybody out there really wants a Fintech system to do what they need that it currently doesn't cover today, please reach out and get in touch, and I'd be happy to talk to you. Thank you very much.
The key thing, the key challenge that Fintech keeps solving and making things fantastic for our industry is when it comes to direct diode bonding. There was a very clear request from Jabil on the UV curing epoxy. Is there anything that you're working on this?
So we offer like a wide range of dispenser technologies, and then we have our own like proprietary ultraviolet curing strategy. So we also know that this is very critical when it comes to active alignment. So we're also kind of dipping our toes into the world of active alignment and trying to understand, epoxy drift during curing, epoxy behavior before and after curing. So at the moment, we don't have any kind of off-the-shelf solution for this. But yeah, we've always faced the same issues, the industry as well, with like epoxy drift and cure drift and this kind of thing.
Travis, congratulations on what you're doing. I know market is booming. I know there are many orders. I know you are doing a fantastic job with this 0.3 micrometer accuracy with passive alignment. Allow me to bring another company that is really doing a huge impact on the semiconductor industry, but is pushing the photonics industry as well. I would like to bring to the table for the first time at an Optica online industry meeting, Catherine Fisher, Head of Business Development from Werner Lieb. Welcome, Werner Lieb, for the first time at an Optica online industry meeting. The floor is yours.
So, thank you very much, and I hope you can see my slides.
Gorilla Glass Clear.
Excellent. So thank you very much for having the opportunity to introduce the company and myself. Let me start. I'm, as you said, the new kid on the block at Optica, but not entirely new to the field. So I started out in micro-optics with Reinhard Völkel, got pulled into semiconductor manufacturing processes and equipment at SÜSS Microtech, and now with Lieb, I'm trying to connect the dots, maybe shaving a little time off the journey from lab to fab. So let's see if we can get close to that within the community. So Lieb is a special machine manufacturer located in the northern part of Bavaria with more than 20 years of experience in building semiconductor equipment and a track record of hundreds of tools in all top manufacturing fabs worldwide. On the left, you can see a typical example of a tool we are building for semiconductor industry, handling wafers from one cassette to another and in between the process module. On the right, you see inside the tool from above, and actually what you can see is nothing. There's a big blue empty space, and so you might ask yourself why it's that empty. The free space is for your process module, giving you the possibility to go to the market with a full automated platform. We integrate your process module and you can concentrate on your process. And by that, we can enable you to transfer your process in light speed from lab to fab. So that's especially when it comes down to wafer level based processes in PICs manufacturing. So quick and short, and I'm happy to get any inquests of who has any interest in kind of getting his perfect technology into an automated platform, which I heard a few times now in all the presentations that this is missing, the automation part, and we would be happy to help here.
Catherine, welcome to Optica. We typically focus on the PIC itself, and having a company that really can match this with handling, transport, and automation to calculate the overall yield is great. You are going to play a fantastic role. We're going to make a lot of introductions, but allow me to bring to the table our closing speaker today. And we actually save something very interesting because we make a living out of collaboration. And many of you saw in the news that Epiphany really is collaborating with many of the global foundries globally, and they recently had an announcement collaborating with NLM Photonics and global foundries offering already access to organic polymers, and we've been definitely waiting for this. Making success out of collaboration, we love this. Jorn Epping, CEO of Epiphany Design, the floor and the attention of everyone is yours. Send us away the way that we deserve.
Thank you very much, Jose. Very rarely I get such a nice welcome, but yeah, I think in photonics, indeed, collaboration is key. Yeah, and that is the collaboration between everything. Yeah? And that is very important point for us because we want to have. First of all, we want to change this slide because it's your vision and our expertise. So we want to bring your expertise and make it available. Yeah? And the first one is what do? We do offer design solutions and supply chain support. So we bridge the whole supply chain where packaging is the first line. Actually, we heard that to shave off the costs. But the first point where you can save that is in the design. Make the right design choices and collaborate with the right partners in order to be, to have a small, design to market to chips. Yeah. And we also do that by making design kits for our customers to make their technology available. And that's also what we are planning and will do with NLM to make their process available. We will also help them developing the PDK for that in order to be accessible. And this all we combine also internally with the hybrid laser design module, for example, where we have pre-tested, validated hybrid lasers that can be packaged and where package is already validated, so you don't have to experiment in the processes there. That, and what we call it always, it's ABCD, it's assembly-based chip design. Because you really want to fit there in standard chip design, what people offer. That's why I asked for Jabil, how can I access you? How can I make chips for you in order to have a smooth transition for our customers? What is very important, of course, is the design verification. Because what brings, for example, and we heard that in many of these talks, bringing EICs and PICs together is very important, and that will be done via design and verification. Why verification? Because you want to be really sure that you're doing the right thing and not lose time and money. So typically we start with the schematic and the simulations and mask layout, and then do the verification. We go all the way back for checking it with DRC. Also do post layout simulation. Is it really what I want to get? And also lately, layout versus schematic to really see, is it what you will get, what you can package such that you can go to the market with your designs. And then let me see that, also verification in design is key for advanced packaging. In order to have what you need, and cross-platform design modules such as hybrid lasers or designing for organics and polymers is key to make technology available. And then thanks a lot. I'm happy to receive any
Thank
questions.
you. Well, thank you, John, for being with us and for what you are doing for the industry. But one key question, and I think many of us had this question in mind whenever we hear the current ecosystem on PDKs, is there a way? Is there a way? Or is there going to be a way in the future that I can actually easily transfer my design from one big foundry, let's call it global, to another big foundry, let's call it tower? Is that going to happen?
Yes, actually, that is what we're doing for our customers. We go one level higher and design agnostic of PDKs, such that indeed the technology transfer from one fab to another is easy.
I would like now to thank everyone. What I'm gonna do is gonna cut the live stream in YouTube. So for that, I have a closing video. For those of you who want to stay for a drink after the event, stay with us and we'll have a nice virtual drink. But now allow me to close the live stream.
This is Optica. This is lighting redefined.
All right, so allow me to ask IT to kindly close the live stream. This becomes now a private event. I can undo my tie and breathe again. And I would like to thank everyone. Oh my God, so many people joined today. For those of you who had to leave because you had to pick up the children, because you had to start working, because